بسم الله الرحمن الرحيم. بنرحب فيكم في المحاضرة رقم 11 في إجراءات إشارية رقمية. اليوم بدنا نتكلم أو نكمل في موضوع ال Discrete Time Fourier Transform، وراح نحكي في بعض الثيورمز اللي بتخصها بحيث إنه نستفيد من هذه الثيورمز في عملية ال Evaluation أو حساب ال Frequency Domain or the signal in the frequency domain, which is the DTFT of the discrete time signals. Okay, so the topic that we are discussing today is discrete time Fourier transform theorems. حتى نبدأ بالtheorems, I'm gonna take two sequences. We're gonna let G of n إلها Fourier transform DTFT يساوي G of E J omega, and another sequence H of n has the Fourier transform DTFT equals H of EJ omega. Based on this, we're going to start taking the theorems one by one. The first one is the linearity theorem. And here, linearity says that if you have a combination of G of n plus some constant G of n times beta, H of n, so you have a linear combination of the two sequences, then because of the linearity of the DTFT, this is supposed to be the same alpha G of EJ omega plus the same beta H of EJ omega. And this is because of linearity and because of the definition of the discrete time Fourier transform. Okay, this is very simple and straightforward. Number two is the time reversal. Theorem. And time reversal, if you have a reverse in time, so instead of G of n, you have G of minus n, so it's flipped 180 degrees. It means that the DTFT of the new signal is exactly the same G with minus sign e to the minus j omega. It's not e to the j omega, it's with every omega inside, you replace it by minus omega and you get the answer. So you don't have to implement the DTFT from scratch. If you know G of n, you fold it 180 degrees, you know that G, the new G is this way. We can take an example just directly. If you have, let's say, a signal like this. So this is 1, 2, and 3, and it starts from 0, 1, and 2. So this signal, if this is my G of n, and I know that, this is your G of n, so my G of n is equal to 1, 2, and 3. My G of E j omega equals to 1 plus 2 e to the minus j omega plus 3 e to the minus j 2 omega. Now, G of minus n is equal to, notice that if you flip this one around the n equals 0 axis, then you have G of minus n to be graphically like this, So you have 1, 2, and 3. 0, minus 1, minus 2. So this is my G of minus n, and this is my n. So G of minus n is equal to 3 2 and 1, and this is your 0. So this is my n equals 0, this is n equals 0, n equals minus 1, and n equals minus 2. And we know that if we call this, just for simplicity, if we call this to be my y of n, so you have y of e j omega equals to, the first one is 3 e to the plus j2 omega plus 2 e to the j omega plus 1. Looking at this and looking at this, so this one and this one, if you replace omega, if you take this one here and say that this g of minus j omega is equal to 1 plus e, 2e, we replace minus omega by minus omega, so you have j omega plus 3e to the j 2 omega. This one and this one are equal. And this is how the time reversal works. Okay? So replacing every omega by minus omega, you find the time reversal. Okay, the third theorem is the time shifting theorem. Time shifting theorem says that if you have g of n minus n0, shift of g of n, then the dt of t is equal to e to the minus j omega n0 g of e j omega. Okay? Looking at this time shifting, notice that this one here is a phase shift. Its magnitude for g of n, or the shifted version of g of n, does not change in the frequency domain. It only has a phase shift added to it. Let's take the following example. If we let y of n equals to alpha to the n for n between 0 and n minus 1, and 0 otherwise, and the magnitude of alpha is less than 1. And we need to find y of e j omega. Okay, to find this, we can write y of n as, when using the unit step functions, we can say that y of n is equal to alpha to the n times mu of n minus mu of n minus m. Yeah, because it's defined, sorry, this one is m minus 1. I'm sorry about this. So this one is m, this one minus m, and this is how we can rewrite this definition. The definition of y of n in two pieces. This one is alpha to the n with all ones between 0 up to n minus 1. After that, you have zeros. So this is how we represent it. Okay, expand alpha to the n, mu of n, minus alpha to the n, mu of n minus m. This one has no problem. We know the answer. This one is a shifted, but it's not totally shifted. This one should be n minus m. So I'm going to put it in the following manner. Alpha to the n, mu of n minus alpha to the m times alpha to the n minus m mu of n minus m. So I added minus m, alpha to the minus m, and alpha to the plus m, which end up to be 1. Alpha to the 0, which is equal to 1. So okay. Now we know the answer of this one. So our y of e j omega is equal to 1 over 1 minus alpha e to the minus j omega. We know the answer previously. Because the magnitude of alpha is less than 1, we use the power series summation. And the second one, we have minus alpha to the m. This is a constant. This part here is a shifted version where n0, my n0 here is equal to m. So n0 equals to m. So we have the same alpha to the n, mu of n, but shifted by m. So we can use this theorem and say that this is e to the minus j omega m over minus alpha e to the minus j omega. So this is equals to, common denominator is the same, 1 minus alpha e to the minus j omega, and up here is 1 minus alpha e to the minus j omega to the power n. So this is my y of g omega. So we use the time shifting property here to prove the answer. We can look at the answer in a different way. You know, if you know that from the example, you know that y of n is equal to alpha for n equal 0, 1, 2, up to m minus 1. So this is a summation, yeah, to do the y of ej omega. This is equals from n equals 0 up to m minus 1, alpha to the n, e to the minus j omega n. And this is up to m minus 1. We know from calculus that, you know, if you are summing r to the n from n equals 0 up to m minus 1, where the magnitude of r is less than 1, this is equals to 1 minus r to the power m over 1 minus r. So if you apply this here, this is equals to summation alpha e to the minus j omega to the power n from n equals 0 up to n minus 1. So this is equals to 1 minus alpha e to the minus j omega, the whole thing to the power m, which is the upper limit plus 1 over the base, alpha e to the minus j omega. Okay? So this one and this one is the same, but we solve it in two different ways. One, we use the time shifting theorem, and one we use the summation of the power series, or geometric series, sorry. Okay, it's the geometric series. This is a geometric series in calculus. So this is the geometric series summation. Okay. We'll take another example and look at it also for the system with the following difference equation. D0, V of n plus b1 v of n minus 1 equals to p0 delta of n plus p1 delta of n minus 1. Find v of e j omega. Okay, in this case, when you have a difference equation like this, we advise you to do the Fourier series for the whole difference equation. So we're gonna do it with using linearity and the time shifting at the same time. So this is d0 v of ej omega plus d1, and this one is a shifted version. So it's e to the minus j omega, and n0 is 1, times v of ej omega equals to p0, and the Fourier transform of the delta is 1, so multiplied by 1, plus p1, and this is the delta is 1, but it's shifted, so this is p1 e to the minus j omega times 1. So we take v of ej omega common, so you have d0 plus d1 e to the minus j omega equals to p0 plus p1 e to the minus j omega. So v of e j omega equals to p0 plus p1 e to the minus j omega divided by d0 plus d1 e to the minus j omega. So this is our Fourier transform of v of ej omega. Okay. Let's move further with the theorems. Now we saw the time shifting. Now we will go to the frequency shifting. So number 4 is frequency shifting theorem. So if we have e to the j omega 0 n x of n, so you have phase shift in time domain, definitely you will have, phase in frequency domain, you will have shift in frequency. So dt of t, you have g of e j omega minus omega 0. Okay? And you have the shift here with the same shift as omega 0 that you have here. Let's have an example, although it's not very typical, but we will take it anyway. Let y of n is equal to minus 1 to the power n, alpha to the n, mu of n, the magnitude of alpha is this one. And also we need to find y of e j omega, the frequency, the dt of t of y of n. Okay, as a solution, y of n can be expressed as y of n equals minus 1 to the power n. We can look at it as e to the j pi n. E to the j pi n is the same as minus 1 to the power n. For odd values of n, this is minus 1. For even values of n, this is equals to 1. So this is y of n times x of n, where x of n is equal to alpha to the n, mu of n, and magnitude of alpha is less than 1. So we represented y of n as e to the j pi n. So this one will look like this, with omega 0 equals to pi. Now, we know that for x of e j omega equals 1 over 1 minus alpha e to the minus j omega. So we have this one, so we have y of e j omega equals 1 over 1 minus alpha e to the minus j omega minus pi, because omega 0 is equal to pi. So we replace every omega by omega minus omega 0. So this is equals to 1 over 1 minus alpha e to the j pi e to the minus j omega. E to the j pi is minus 1, so this is equal 1 over 1 plus alpha e to the minus j omega. Okay? So this is the answer. Actually, this is a long way to do it. You can think of this one. Minus 1 to the power n alpha to the n is minus alpha to the n mu of n. Minus alpha to the n mu of n, if you substitute it here, so it will be 1 minus alpha e to the minus j omega, and you end up with the same answer. So this answer is okay. Okay. The fifth theorem is differentiation. Differentiation in frequency. Differentiation in frequency says that if you have a sequence n g of n, not g of n only, n times g of n has the dt of t, which is equal to j times the derivative of ej omega by d omega. Okay? And this is easy to show. If you take the definition, proof for this property or this theorem, if you take g of ej omega by the definition, which is equal to summation from n equals minus infinity to infinity, g of n e to the minus j omega n, and you differentiate both sides with respect to omega, then you have here d g of ej omega by d omega equals to summation. The integration will go inside and we differentiate with respect to omega, so this one will be minus j n g of n e to the minus j n from n equals minus infinity to infinity. Okay, now if we multiply both by j, so you have on this side j dj of ej omega by d omega, which is what we have here. This is equals to the definition of the sum, the Fourier of the following sequence. Summation from minus infinity to infinity, j times minus j is equal to 1. So this one is n, g of n e to the minus j omega n. So this is a frequency domain, this is a time domain, and this is our sequence that we are doing the Fourier transform of. So the Fourier transform of n g of n is this one, as we show here. Okay. As an example, let's take the sequence, consider the sequence y of n equals to n plus 1 times alpha to the n mu of n, and the magnitude of alpha is less than 1. I'm gonna let, what we need here is find y of e j omega. I'm gonna let x of n, y of n equals to n x of n plus x of n, where x of n is equal to alpha to the n mu of n, and the magnitude of alpha is less than 1. So we expand this one. We rename alpha to the n mu of n as x of n, and we put it in this form. Now, x of e j omega, as we know, it's 1 over 1 minus alpha e to the minus j omega. So the second part is okay. This part here, we go to the differentiation in frequency, and we need to find j dx of e j omega by d omega, and this is equals to j times, inside this one is the differentiation of this one with respect to frequency is e to the minus j omega squared, and you have a minus sign. You have a minus sign here, minus sign here, 3 minuses. So you have minus j alpha e to the minus j omega. And if you multiply j times minus j, you end up with alpha e to the minus j omega over 1 minus alpha e to the minus j omega, the whole thing squared. So this one is the Fourier transform of nx of n. The Fourier transform of x of n is this one, so we have to add them and find the answer. So our final answer will be the summation of those two terms. So my y of e j omega is equal to j dx of e j omega by d omega plus x of e j omega. The Fourier transform of this one here, which is equal to alpha e to the minus j omega over 1 minus alpha e to the minus j omega squared plus 1 over 1 minus alpha e to the minus j omega. Common denominator is 1 minus alpha e to the minus j omega squared. The first one is alpha e to the minus j omega plus 1 times 1 minus alpha e to the minus j omega. This one subtracted from this one, and we end up with 1 over 1 minus alpha e to the minus j omega squared. So we have Fourier transform for y of n, so n plus 1, we can put it in this form, n plus 1 times alpha to the n mu of n, where alpha magnitude less than 1 has the dt ft equals to 1 over 1 minus alpha e to the minus j omega squared. Okay, so this is Fourier transform pair, and this is a nice property. Okay. Property number 6 is the convolution theorem. And this is really one of the most important theorems in Fourier transform because it makes convolution very easy in frequency domain. G of n convolve with h of n in time domain. It is only multiplication in frequency domain. So this is G of E j omega times h of G j omega. So convolution in time domain, it's multiplication in frequency domain. So one application of this theorem is that you can implement the convolution by forming the product of G of E j omega times h of E j omega, and then computing the inverse Fourier transform of the product. Okay? Symbolically, we can put it in, we can say that we have dt of t for G of n, dt of t for h of n. You get the result here as G of E j omega. Get the result here as h of E j omega. Put them as multiplication. You get here y of E j omega, which is equal to the G of E j omega times h of E j omega. So and you go here and you find the inverse dt of t, and you find here y of n, which is equal to the convolution of G of n convolve with h of n. Okay? So this is here. Okay. I'm going to take a simple example to demonstrate the idea. Let me take a simple example. Let G of n equals to 1, 2, and 3, and h of n equals to 1.5 and 0.3. And you have the 0 here and the 0 here. We don't. So the arrows are underneath the first element, and we need to find y of n, which is equal to G of n convolve with h of n. Okay? Okay. I'm going to do this using two methods. The first one is the tabular method. And the tabular method, we have to put n. So you have G of n is equal to 1, 2, and 3. So I have 0, 1, 2, 3, 4, 5, and so on. And the second sequence is h of n, which is equal 1.5 and 0.3, sorry, 0.3. Okay, now we start implementing. I'm going to take the first element, multiply it by the whole sequence, 1 times 1, 1 times 2, 1 times 3. Now you take one space, 0.5, 0.5 times 2, 1, 0.5 times 3, 1.5. Then we take 2 steps, 0.3, 0.3 times 2, 0.6, 0.3 times 3, 0.9. And we end this and we start summing 1, 2.5, 4.3, 2.1, and 0.9. And this is our y of n is equal to this, and here is your 0 actually. Okay, so this is the answer using the real convolution. Now to do this through using the convolution theorem, we have g of e j omega equals to 1 plus 2e to the minus j omega plus 3e to the minus j2 omega, and h of e j omega equals to 1 plus 0.5 e to the minus j omega plus 0.3 e to the minus j2 omega. Now if you multiply g of e j omega times h of e j omega, we'll take the first element, multiply it by g, take the second element, multiply it by g, take the third element, multiply it by g. So you have the first one is 1 plus 2e to the minus j omega plus, so I'm multiplying the 1 here by the whole g plus 3e to the minus j2 omega. Next, I'm going to take the second element, multiply it by g. So you have plus 0.5 e to the minus j omega plus 0.5 times 2, which is 1 times e to the minus j2 omega, plus the last one is 0.5 times 3, 1.5 e to the minus j3 omega. And the last element here multiplied by the whole elements in g. So this is plus 0.3 times 1, 0.3 e to the minus j2 omega plus, so this is a multiplication of polynomials actually. So you can think of this polynomial as e to the minus j, or e to the j omega is the core of the polynomial, and these are the powers of it. E to the minus j omega is call it x, so you have this one x squared, x squared, and so on, and this one is x to the power 0. So 0.3 times this one, 0.3 times 2, it's 0.6 e to the minus j3 omega, and the last one is 0.9 e to the minus j4 omega. If we add them, so you have to add them as a polynomial. This is 1 plus 2.5 e to the minus j omega plus 3 plus 1 plus 0.34, 0.3 e to the minus j2 omega plus 1.5 plus 1.6 with the same power, 2.1 e to the minus j3 omega plus 0.9 e to the minus j4 omega. By inspection, if you look at this function or polynomial in e to the minus j omega, You can reverse this into the time domain very easily by looking at the powers here, because they represent the indices of y of n. So I can directly say that y of n is equal. What is the, this is e to the j0, so index is 0. So this is my 1. This is index of 1, so this is 2.5, 4.3, 2.1, and 0.9, and our 0 is here. So I did the inverse here directly from looking by inspection. By inspection. Okay? Now, somebody will ask me if this tabular method is much easier than this one, multiplication of polynomials. Our answer to this is that if you want to do the tabular method using computers, definitely it's much easier to go in the computer, do the Fourier transform for the first sequence, the Fourier transform with the second, multiply in frequency, multiply them in MATLAB, and then do the inverse. It's much easier to do it than the tabular method. So sometimes in the analytical way to do things, it's easy to do it in some way, but if you want to do it by programming, you have to do it in another way. Okay, number 7, modulation theorem. And this is the dual of the convolution. So if you have multiplication in time domain, you have a convolution in frequency. Okay, so this is equals to 1 over 2 pi integration from minus pi to pi g of ej theta h of ej omega minus theta d theta. Okay? The second, or the term on the right-hand side is the convolution over one period in the frequency domain. So you convolve from minus pi to pi of this function in the frequency domain. Usually we don't need this much, except when we go for the Gibbs phenomena, when we talk about the truncation of some of the impulse response functions. We'll see this when we discuss filters later on. Okay, number 8 is the Parsifads relation. And the Parsifads relation says that if you have a summation in the time domain from n equals minus infinity to infinity, g of n times h complex conjugate of n, this is equals to 1 over 2 pi integration from minus pi to pi g of e j omega times h complex conjugate of e j omega d omega. Notice that the Parsifads relation is not Fourier transform pair, it's equality. So please be careful about this. It's equal. It's not the Fourier transform pair. This one in frequency in time domain equals to this in frequency domain. Now if g of n is equal to h of n, then this one will be multiplied by its complex conjugate, and the whole thing will be like this. From n equals minus infinity to infinity, magnitude of g of n squared is equal to 1 over 2 pi integration from minus pi to pi g of e j omega magnitude squared d omega, which means that if this one, if g of n is an energy sequence, then this one is finite. You can find it in time domain and you can find it in frequency domain, which means that the energy of the sequence is a fixed value. Whether you represent the sequence in time domain or you present it in frequency domain, calculating the energy should be the same. The energy does not change if you are looking at the sequence from time domain perspective or frequency domain perspective. Okay? Okay, can we take an example? Let's take an example for this one. Let's take a very simple example. Let g of n equals to 1, 2, and 3. Okay? And we need to find let's see, the energy of G using Parsifads relation. Okay, first let's find E sub G, which is equal to G sub n, or G of n squared, from n equals minus infinity to infinity. But here we have only 3 elements, so this is 1 squared plus 2 squared plus 3 squared, and this is equals 1 plus 4 plus 9, this equals 14. 14 units of energy, microjoule, nanojoule, joules, we don't care. Okay, now I'm gonna go and find it through this one. So what is G of E? J omega, which is equal to 1 plus 2e to the minus j omega plus 3e to the minus j 2 omega. What is the magnitude of E j omega squared? This is equals to j omega times G complex conjugate of E j omega. This is equals to 1 plus 2e to the minus j omega plus 3e to the minus j 2 omega times the complex conjugate of this one is 1 plus 2e to the j omega plus 3e to the j 2 omega. This is the complex conjugate of those two complex quantities. This one is real, so its complex conjugate is the same. This one magnitude, and this is the phase, so the opposite of the phase, the opposite of the phase. So we have those two multiplied. So those two are polynomials multiplied by each other. So we will end up with multiplication of this one, 1 plus 2e to the minus j omega plus 3e to the minus j 2 omega. And the second one will be multiplied by those, so 2e to the j omega plus 4 plus the last one is 6e to the minus j omega. The third one plus 3e to the j 2 omega plus 6e to the j omega. And the last one is 9e to the j 0. So those are the values that we will get. If we combine those together, we can see that we have some real values and we have some complex values with their complex conjugates. Now we have 1 plus we have 4 plus 9. So you have 3 values, this one, and this one. Now we have also 2e to the j omega, and we have 6e to the j omega. So you have plus 8 times e to the j omega plus, you have another 8 with e to the minus. You have this one here, and you have this one here. So this is e to the minus j omega. 8e to the j omega, 8e to the minus j omega together. And the last one is e to the minus j2 omega, e to the minus j2 omega. So this is plus 3 e to the j2 omega plus e to the minus j2 omega. So the magnitude of g of e j omega squared is equal to 1 plus 4 plus 9 plus 16 cosine omega plus 6 cosine 2 omega. Implementing EG equals 1 over 2 pi, the integration from minus pi up to pi, magnitude of EJ omega squared d omega equals to 1 over 2 pi, integration from minus pi to pi, 1 plus 4 plus 9 plus 16 cosine omega plus 6 cosine 2 omega, the whole thing d omega. Now those are 1 plus 9 plus 4, they are constants. They add up to be 14. D omega, they are omega with 2 pi. So you have at the end 16 cosine. Cosine omega from minus pi to pi is 0. It's the integration, and this one is also 0. So we end up with 1 over 2 pi times 14, it's not 16. 9 plus 4 plus 1, 14 times 2 pi and 2 pi again. And we end up with 14, which is the same answer that we got here. Okay, so those are most of the very popular theorems about the DTFT. I hope that you will find this lecture interesting, and I will see you in the next one. Thanks.